Now let us apply the method of images to determine the electric field due to some systems involving a point charge. The first example for such a system is a positive point charge q at the distance x sub plus from the center of a conducting sphere of radius capital R at zero potential. If the distance x sub plus is greater than the radius capital R, the point charge q is outside the sphere as seen in the figure, otherwise the point charge is inside the sphere. In both the cases, the field lines emanating from the point charge and terminating at the conducting sphere are perpendicular to the surface of the sphere since it is an equipotential surface. When we determine the electric field due to the charge q and the induced charge on the grounded sphere, the volume of interest V is the domain outside the sphere in the first case, and the domain inside the sphere in the second one. In this boundary value problem we need to find the potential that vanishes over the sphere representing the boundary of the volume of interest V. We will use the method of images to replace the boundary value problem with another one by extending the volume of interest V with the volume V' either inside or outside the sphere, and place a negative charge q' in the volume V' at the distance x sub minus from the center of the sphere. The superposition of the electric fields due to the point charge q and the image point charge q' is the solution of the boundary value problem over the volume of interest V, provided it gives a zero potential over the grounded sphere. This condition can be used to determine the distance x sub minus and the amount of charge q' for given values of the distance x sub plus, the radius capital R and the amount of charge q. The electric potential phi due to the charge q and its image charge q' is given by the sum of the potentials generated by each of the point charge, that is the potential phi at the point P is equal to 1 over 4 pi times the vacuum permittivity epsilon naught, times the charge q over the distance R sub plus of the point charge q from the point P, plus 1 over 4 pi times epsilon naught, times the charge q' over the distance R sub minus of the image point charge q' from the point P. If theta denotes the angle between the x-axis and the direction of the point P from the center of the sphere, then we can apply the law of cosines, and write the square of the distance R sub plus as the square of the distance R of the point P from the center of the sphere, plus the square of the distance x sub plus between the point charge q and the center of the sphere, minus 2 times R times x sub plus times cosine theta. Similarly, the square of the distance R sub minus can be written as R squared, plus the square of the distance x sub minus between the point charge q' and the center of the sphere, minus 2 times R times x sub minus times cosine theta. Now we apply the condition stating that the potential phi over the surface of the sphere must vanish, that is the sum of the two fractions is equal to 0 when it is evaluated at the points for which the distance R is equal to the radius capital R of the sphere. The condition reduces to the equation stating that q over R sub plus evaluated at the radius capital R is equal to q' over R sub minus evaluated at the radius capital R. Since we express the squares of R sub plus and R sub minus in the terms of the distance R, we will take the square of this equation and use the condition stating that q squared over R sub plus squared must be equal to q' squared over R sub minus squared when both fractions are evaluated at the radius capital R. We note that this operation increases the number of the roots of the equation describing the condition, and we need to select the one that has a physical meaning. By substituting the expressions obtained for the distances R sub plus and R sub minus into the condition, we can write the equation stating that q squared times the quantity of capital R squared plus x sub minus squared minus 2 times capital R times x sub minus times cosine theta, is equal to q' squared times the quantity of capital R squared plus x sub plus squared minus 2 times capital R times x sub plus times cosine theta. This is a general condition which holds for any angle theta. Then it must be true for a given value of theta as well, and we can choose some convenient value to reduce the equation to a simpler form. For theta equals pi over 2, cosine theta vanishes and the condition becomes the equation stating that q squared times the sum of capital R squared and x sub minus squared is equal to q' squared times the sum of capital R squared and x sub plus squared. For vanishing theta, cosine theta is equal to 1 and the condition can be written as the equation stating that q squared times the square of the difference between capital R and x sub minus is equal to q' squared times the square of the difference between capital R and x sub plus. Now we have two equations with the unknown quantities x sub minus and q', which will be solved for these two quantities if x sub plus, capital R and q are given. We can eliminate q and q' from these equations by dividing the first equation by the second one, and simplify the result by multiplying the fractions on both sides by the product of their denominators. After expanding the square of the sums and further simplifying the result, we obtain a second-order algebraic equation in the distance x sub minus of the image point charge from the center of the sphere stating that x sub minus squared, minus a constant b times x sub minus, plus capital R squared is equal to 0, where b is defined by x sub plus times the quantity of 1 plus the square of the ratio of capital R to x sub plus. The roots of the second-order algebraic equation are then given by b over 2, plus or minus 1 over 2 times the square root of the difference between b squared and 4 times capital R squared. As already mentioned, we need to drop one of the roots of this equation since it is non-physical. The position of the image point charge q prime described by the distance x sub minus must be in the volume v prime complement to the volume v enclosing the point charge q. If we choose the negative sign, then this condition holds and the position of the image point charge described by its distance x sub minus of the from the center of the grounded sphere can be written as the square of the radius capital R of the sphere over the distance x sub plus. Now we can substitute this result into the first condition of the pair obtained by fixing the angle theta, and express the amount of the image point charge q prime as minus the ratio of the radius capital R to the distance x sub plus, times the amount of the point charge q. The negative sign indicates that the inducing charge q and the image charge q prime always opposite charges. These formulae hold for both the cases. The image charge q prime is always placed in the volume v prime outside the region of interest, regardless of whether the charge q is located outside or inside the sphere. The distance x sub minus of the image charge from the center of the sphere has a similar scaling property with the radius and the distance of the inducing charge from the center as the one found in the case of a uniformly charged infinite line near an infinite conducting cylinder. The ratio of the radius capital R to the distance x sub shows that the point charge located outside the sphere has always the greater magnitude, regardless of whether it is the inducing charge or the image charge. The different magnitudes for charge indicate that not all the electric field lines emanating from the point charge placed outside terminate at the sphere. Some of them go around the sphere and terminate at infinity. We note that as the inducing charge q is brought closer to the sphere, the image charge q prime grows in magnitude and moves from the center of the sphere towards its surface. When the point charge q is just outside the surface of the sphere, the image charge q prime is equal and opposite in magnitude and lies just beneath the surface. By applying the method of images, we have determined the electric potential due to the point charge near the grounded sphere in the volume of interest V, which allows us to calculate the electric field strength expressed as the negative gradient of the potential in a spherical coordinate system with the origin at the center of the sphere and the angle theta chosen as its polar angle. The negative gradient of the electric potential phi has the following form. The radial component of the electric field strength E is given by minus the partial derivative of the potential phi with respect to the radial coordinate r. Its polar component is equal to minus 1 over the radial coordinate r, times the partial derivative of the potential phi with respect to the polar angle theta, and its azimuthal component is given by minus 1 over r times sine theta, times the partial derivative of the potential phi with respect to the azimuthal angle phi. As already seen, the electric potential phi of the system at a given point P is the superposition of the Coulomb potentials due to the positive inducing charge and the negative image charge, where the potentials are inversely proportional to the distance r sub plus and r sub minus of the point charges from the point P. The square of the distance r sub plus or minus is equal to r squared plus x sub plus or minus squared, minus 2 times r times x sub plus or minus times cosine theta, as seen in the figures. Then we can derive the components of the electric field strength by computing the partial derivative of r sub plus or minus raised to the power of minus 1. By inserting the expressions for r sub plus and r sub minus into their partial derivative with respect to the distance r, we can write it as minus the ratio of r minus x sub plus or minus, times cosine theta to the cube of r sub plus or minus. Similarly, the partial derivative of the r sub plus or minus raised to the power of minus 1 with respect to the polar angle theta, is given by minus the ratio of r times x sub plus or minus, times sine theta to the cube of r sub plus or minus. If we substitute this result into the negative gradient of the potential phi, the components of the electric field strength E can be written as follows. Its radial component is equal to 1 over 4 pi times epsilon naught, times the sum of the distance r minus the distance x sub plus times cosine theta over the cube of the distance r sub plus times the charge q, and the distance r minus the distance x sub minus times cosine theta over the cube of the distance r sub minus times the charge q prime. Its polar component is given by 1 over 4 pi times epsilon naught, times the sum of x sub plus sine theta over the cube of the r sub plus, and x sub minus sine theta over the cube of the r sub minus. Its azimuthal component vanishes since the potential does not depend on the azimuthal angle phi. In order to summarize our findings, we show the potential phi given by the sum of the potentials due to the point charges q and q prime again, together with the expressions of the distance x sub minus of the image charge from the center of the sphere and the amount q prime of the image charge in the terms of x sub plus, capital R and q. The vanishing azimuthal component of the electric field and the independence of these equations of the azimuthal angle shows the axial symmetry of the electric field about the axis connecting the 2 point charges with each other, that is about the x-axis passing through the point charge q and the center of the grounded sphere. We can also determine the electric field strength E at the surface of the sphere. The distance x sub minus of the image charge q prime from the center of the sphere, that is from the origin of the spherical coordinate system, was expressed as the square of the radius R of the sphere divided by the distance x sub minus of the inducing charge q from the center of the sphere. If we suppose that the point P is located on the surface of the sphere and applying this equation, we can write the distance r sub minus of the point P from the image charge q prime as the ratio of r to x sub plus, times the distance r sub plus of the point P from the inducing charge q. Since the image charge q prime is also given by the ratio of r to x sub plus times the charge q, we can substitute these two equations into the components of the electric field strength E to describe the electric field over the surface of the grounded sphere. Then we find that the radial component of the field is given by 1 over 4 pi times epsilon naught, times q over the cube of r sub plus times capital R, times the difference between capital R squared and x sub plus squared while its angular components vanish. This result confirms that the electric field lines are perpendicular to the equipotential surface of the grounded sphere, as we expected. We can also apply the theory of images together with Coulomb's law to determine the force exerted by the charge q on the sphere with its induced charge represented by the image charge q prime. Since the distance between the inducing charge q and the image charge q prime is given by the difference between the distances x sub plus and x sub minus, the component of the electrostatic force F acting between the point charges in the direction of the x-axis is equal to 1 over 4 pi times epsilon naught, times the product of the charges q and q prime divided by the square of the difference between x sub plus and x sub minus. If we insert the expressions obtained for x sub minus and q prime into the right-hand side of the equations, then we obtain minus 1 over 4 pi times epsilon naught, times x sub plus times capital R times q squared over the square of the difference between x sub plus squared and capital R squared. The formula shows that the electrostatic force is an inverse cube law for large separation of the point charge q from the grounded sphere, where the ratio of capital R squared to x sub plus tends to 0. If the inducing point charge is close to the sphere, that is the ratio of capital R to x sub plus tends to 1, then the electrostatic force is proportional to the inverse square of the distance away from the surface of the sphere. As we have already seen, the surface charge density over an equipotential surface is given by the vacuum permittivity times the normal component of the electric field at the surface. Now we use this relationship to determine the surface charge density and the total induced charge over the grounded sphere near the point charge. The surface charge density sigma is evaluated over the equipotential surface given by the radial coordinate r equals the radius capital R of the sphere, and the normal component of the electric field E is equal to its radial component at the surface of the sphere. If we substitute the radial component of E obtained by evaluating the electric field strength at the radius capital R, then we can express sigma as the charge q over 4 pi times capital R, times the difference between the square of capital R and the square of x sub plus, over the quantity of the square of capital R plus the square of x sub plus minus 2 times capital R times x sub plus times cosine theta, raised to the power of 3 over 2. The angular dependence of both the radial component of the electric field strength and the distribution of the electric charge density over the surface of the sphere indicates that the charge distribution is not necessarily uniform over an equipotential surface but always static, as seen in the case of the previous examples of electric fields with cylindrical equipotential surfaces. The total induced charge over the surface of the grounded sphere can be obtained by integrating the surface charge density sigma over its surface, where the surface area element is given by 2 pi times the square of the radius capital R times sine theta times d theta, and the expression is integrated with respect to the polar angle theta from 0 to pi. If we substitute the expression derived for the surface charge density sigma into the integral, then we can write the total charge over the sphere as q over 2 times the difference between capital R squared and x sub plus squared, times the integral of capital R times sine theta over the cube of R sub plus evaluated at capital R with respect to theta from 0 to pi. As the figures illustrating the two cases show, the square of R sub plus is equal to R squared plus x sub plus squared minus 2 times R times x sub plus times cosine theta. The differential of R sub plus evaluated at capital R is therefore given by capital R times x sub plus over R sub plus evaluated at capital R, times sine theta times d theta. We can use this expression to replace the variable theta of the integration by r sub plus, and write the total charge as q over 2 times the difference between capital R squared and x sub plus squared over x sub plus, times the integral of 1 over r sub plus squared with respect to r sub plus from r sub plus evaluated at r equals capital R and theta equals 0, to r sub plus evaluated at r equals capital R and theta equals pi. The primitive function of the integral is given by minus 1 over r sub plus evaluated at the lower and upper limits of the integral. The evaluation of the primitive function gives minus the difference between 1 over the square root of the quantity of capital R squared plus x sub plus squared plus 2 times capital R times x sub plus, and 1 over the square root of the quantity of capital R squared plus x sub plus squared minus 2 times capital R times x sub plus. Then the terms in the brackets can be written as the difference between 1 over capital R plus x sub plus, and 1 over x sub plus minus capital R. If we simplify this expression, then we find that the total charge over the surface of the grounded sphere is equal to minus the radius capital R over x sub plus, times q, that is the image q prime, as we expected. We note that in the two cases of the induced charge outside or inside the sphere, the sign of the surface charge q prime and the direction of the electric field E are opposite over the sphere, as in the previous examples of charged lines and conducting cylinders producing electric fields with cylindrical equipotential surfaces. Now we use the results obtained for a point charge near a grounded sphere to solve another problem by replacing the sphere with a plane. We can determine the electric field due to the point charge q at the distance x0 from a grounded plane as the limiting case of the previous problem if the radius of the grounded sphere becomes infinite. The electric field lines emanating from the point charge q terminate at the grounded plane and they are perpendicular to the phi equals 0 surface, that is, the field lines are parallel with the x-axis at x equals 0. The family of the equipotential surfaces enclosing the point charge approach the vertical plane of the grounded plane at x equals 0 as the electric potential phi tends to 0, and the grounded plane represents the boundary condition for the problem considered in the volume of interest V. As in the previous problem with the grounded sphere, we apply the method of images by dropping the boundary condition and supplementing the volume of interest with the volume V' enclosing the image charge q' located on the x-axis. This problem can be considered as the limiting case of the previous one where the radius capital R of the grounded sphere tends to infinity, and the distance x sub plus of the point charge q from the center of the sphere also becomes infinite. Then the relation stating that distance x sub plus is equal to the distance x0 plus the radius capital R still holds. We can evaluate the amount of the image charge q' given by minus capital R over x sub plus, times q in this limit, where x sub plus is given by capital R plus x0. The fraction can be written as 1 over 1 plus x0 over capital R, which becomes minus q since the limit of the fraction is equal to 1. We also evaluate the distance x sub minus of the image charge q' from the center of the infinite sphere given by capital R squared over x sub plus. Here x sub plus is equal to the sum of capital R and x0, and the fraction can be written as capital R times the quantity of 1 over 1 plus the ratio of x0 to capital R. Since x0 over capital R vanishes as capital R approaches infinity, we can apply the Taylor expansion of the fraction at x0 over capital R at 0. Then we have capital R times the alternating sum of 1, x0 over capital R, x0 over capital R squared, x0 over capital R cubed and so on. If we multiply each term in the infinite sum by capital R, then all the terms vanish as capital R tends to infinity, except the first two terms, which gives capital R, minus capital R times x0 over capital R, that is capital R minus x0. These two expressions evaluated at the limit of capital R of the grounded sphere approaching infinity show that in comparison with the magnitude and the position of the inducing charge q, the image charge q' is of equal magnitude but opposite polarity and symmetrically located on the opposite side of the grounded plane. The reflection symmetry of the point charges around the grounded plane illustrates why this approach to derive the solution of Poisson's equation of simple boundary value problems is called the method of images. Now we determine the electric field at a given point P at the distance r sub plus and r sub minus from the point charges q and q'. We will use the cylindrical coordinate system to describe the electric field because of its axial symmetry about the x-axis. The radial coordinate ρ of the point P is given by its distance from the symmetry axis, and the x-coordinate plays the role of the vertical coordinate normally denoted by z. Then the square of the distance r sub plus between the point P and the point charge q is equal to ρ squared, plus the square of the sum of x and x0. Similarly, the square of the distance r sub minus between the point P and the image charge q' is equal to ρ squared, plus the square of the difference between x and x0. As in the previous problems where the method of images is applied by introducing an image charge, the electric potential phi at the point P given by the superposition of the Coulomb potentials of the point charges Q and Q prime is equal to 1 over 4 pi times epsilon naught, times Q over R sub plus, minus 1 over 4 pi times epsilon naught, times Q over R sub minus. Here we substituted minus Q for the amount of charge Q prime, and the distance R sub plus or minus is equal to rho squared plus the square of x plus or minus x naught. Since the electric field strength E is the negative gradient of the electric potential phi, we will determine its components in the cylindrical coordinate system adapted to the symmetry of the problem. The radial component of the electric field is equal to minus the partial derivative of phi with respect to rho. The azimuthal coordinate of E is given by minus 1 over rho times the partial derivative of phi with respect to the azimuthal angle phi about the symmetry axis, whereas its vertical coordinate is equal to the partial derivative of phi with respect to the axial coordinate z, which is denoted by x in this problem. First we calculate the partial derivative of R sub plus or minus raised to minus 1 with respect to the radial coordinate rho, which gives minus rho over the cube of R sub plus or minus. Then we determine the partial derivative of R sub plus or minus raised to minus 1 with respect to the x coordinate, and we obtain minus the ratio of x plus or minus x naught to the cube of R sub plus or minus. By substituting these equations into the negative gradient of the potential, the electric field strength E at the point P due to a point charge Q at the distance x naught from a grounded plane can be written as Q over 4 pi times epsilon naught, times a vector with the following components in the cylindrical coordinate system with the axis passing through the point charge and perpendicular to the plane. The radial component of the vector is equal to the difference between the distance rho of the point P from the symmetry axis over the cube of the distance R sub plus between the point P and the point charge Q, and rho over the distance R sub minus of the point P from the image charge Q prime. The azimuthal component of the field vanishes due to its axial symmetry, whereas its vertical component is given by the difference between the x-coordinate of the point P plus x naught over the cube of R sub plus, and x minus x naught over the cube of R sub minus. Since the distance R sub plus is equal to the distance R sub minus for x equals 0, we can immediately see from this expression that the radial component of the electric field vanishes at x equals 0, that is, the field is perpendicular to the plane as required. As it was seen in the previous examples, the surface charge density of the induced charge over the infinite grounded plane is given by the product of the vacuum permittivity and the normal component of the electric field. That is, the surface charge density sigma evaluated at x equals 0 is equal to minus epsilon naught times the x component of the electric field strength evaluated at x equals 0. The minus sign is applied here since the surface normal points in the negative x direction. If we determine the electric field E over the grounded plane, that is, for the vanishing x-coordinate, then its component pointing in the direction of the x-axis can be written as q over 2 pi times epsilon naught, times x naught over R sub plus cubed at x equals 0. By substituting this expression into the equation, we can evaluate R sub plus at x equal in the dominator of the fraction. Since R sub plus squared is equal to rho squared plus the square of the sum of x and x naught, R sub plus at x equals 0 reduces to the square root of the sum of rho squared and x naught squared, and we obtain minus q over 2 pi, times x naught over the square of the distance rho plus x naught squared to 3 over 2. This formula shows that the density of the induced charge on the infinite plane has a maximum at rho equals 0, that is at intersection of the x-axis and the plane, and decreases with the distance rho from the point of intersection. The total charge on the grounded equipotential plane can be obtained by integrating this surface charge density over the whole planar surface. Here the area element of the integral expressed in cylindrical coordinates is equal to 2 pi times the square of the radial coordinate rho times d rho. If we insert the expression obtained for sigma at x equals 0 into the integral, then the total charge over the plane can be written as minus q, times the integral of x naught over R sub plus cubed at x equals 0, times rho with respect to rho from 0 to infinity. Since the differential of R sub plus at x equals 0 is given by rho over R sub plus, times d rho, we can apply this result to change the variable rho of the integration to the distance R sub plus. Then we can write the right-hand side as minus q times x naught, times the integral of 1 over R sub squared at x equals 0 with respect to R sub plus at x equals 0, where the lower and upper limits of the integral are R sub plus at rho equals 0 and x equals 0, and R sub plus at rho equals infinity and x equals 0. The primitive function of the integral is equal to minus 1 over R sub plus at x equals 0 evaluated at the lower and the upper limits. The evaluation gives minus the limit of 1 over the sum of rho squared and x naught squared as rho tends to infinity, plus 1 over x naught. Since the first term in the brackets vanishes at infinity, the total induced charge over the infinite grounded plane is equal to minus q. This results means that every electric field line that leaves the point charge q terminates somewhere on the infinite plane, that is, no electric flux escapes to infinity. Since the induced charge is equal to the image charge, the electrostatic force exerted on the grounded planar surface can be derived from Coulomb's law, where the force F between the inducing charge and the image charge located on the x-axis at the distance 2 times x0 from each other is equal to -1 over 4 pi times epsilon naught, times q squared over the square of 2 times x0. The force points from the image charge or the plane towards the inducing charge q. Then the Coulomb force F parallel with the x-axis can be written as -q squared over 16 pi times epsilon naught times x0 squared. We already determined the electrostatic forces between line charges and various conducting surfaces or between a point charge and a grounded sphere. In this example we discuss a simple situation of a point charge exerting force on a grounded infinite plane, where the later can represent the metal plate of an electrode. This simple setup allows us to analyze the role of the electrostatic force between the image charge and the induced charge on the electrode, and we can see that this force prevents the charged particles, in this case electrons, from escaping from the surface of a conductor in electric field. If we apply a uniform electric field E0 on the grounded plane or the plate of the electrode, then a negative surface charge arises over the surface of the electrode, where the field line terminates as there is no electric field in the conductor. By supposing that the electric field lines of the field E0 are perpendicular to the metal plate and point outward from the plane of the electrode, we can write the net force acting on any charged particle q emitted from the surface of the electrode as the difference between the electric force represented by the external field E0, and the Coulomb force due to the image charge -q appearing in the opposite side of the conducting surface at the same distance pulling the emitted particle back. That is, the net force is equal to epsilon naught times the magnitude of the electric field E0, -1 over 4 pi times epsilon naught, times q squared over the square of 2 times x0. Now x0 denotes the instantaneous distance of the inducing charge and the image charge from the surface of the electrode. At the distance where the net force vanishes, the Coulomb force due to the image charge become balanced with the external electric field. This distance, representing a threshold, can be expressed as the square root of the amount of charge q over 16 pi times epsilon naught times the magnitude of the electric field E0. If the distance of a charge carrier emitted from the surface of the electrode from the surface is less than this threshold, the net force points towards the surface pulling back the charge carrier. This effect can be associated with the binding energy of electrons trapped in the surface of a conductor on which an electric field is applied. The external field can be strong enough to accelerate electrons beyond this barrier and they will able to escape from the conducting surface. When the electric field E0 becomes sufficiently large, the electrostatic force exerted on the electrons close to the surface of the electrode can overcome the quantum mechanical binding forces holding the electrons within the electrode. We used the example of a point charge near a grounded sphere to derive the electric field due to a point charge near a grounded plane as its limiting case. We can generalize this example by applying a conducting sphere either with constant electric charge or constant voltage. First we consider the case with the sphere of constant charge q0, where the point charge q in the volume V is outside the sphere of radius R at the distance x sub plus from the center of the sphere. By applying the method of images, we placed an image charge q' inside the grounded sphere with the volume V' at the distance x sub minus from the center on the x-axis connecting the point charge q with the center. We saw that the distance x sub minus is equal to the square of the radius R over the distance x sub plus, whereas the image charge q' is given by minus the ratio of R to x sub plus, times q. Since the total amount of charge on the sphere is equal to q0, we need to introduce another image charge to produce an electric field over the union of the volumes V and V' such that the conducting sphere is still an equipotential surface and has a constant charge q0. If we place a new image charge q" in the center of the sphere, we can apply Gauss's law to determine the amount of the second image charge by using the sphere as a Gaussian surface. The electric flux due to the charge q0 on the Gaussian surface must be the same as the one produced by the total amount of image charges inside the sphere. That is, the charge q0 must be equal to the sum of the image charges q' and q', replacing the charged boundary surface in the method of images. If we substitute the result obtained for q' into this sum, we can express the image charge q' as the surface charge q0 of the sphere, plus the radius R of the sphere over the distance x sub plus, times the charge q. The electric potential due to the 3-point charges is given by the superposition of the Coulomb potentials of the individual charges. Then the potential phi at the point P at the distances R sub plus, R sub minus and R from the inducing charge q, the image charge q' and the image charge q' can be written as 1 over 4 pi times epsilon naught, times q over r sub plus 1 over 4 pi times epsilon naught times q prime over r sub minus plus 1 over 4 pi times epsilon naught times q double prime over r. As seen in the figure, the square of the distance r sub plus or minus is equal to the square of the distance r plus x sub plus or minus squares, minus 2 times r times x sub plus or minus times cosine theta. We already saw that the sum of the first two terms of the potential vanish over the sphere for the expressions for x sub minus and q prime shown here. Then the potential phi over the charged sphere is given by 1 over 4 pi times epsilon naught times q double prime over capital R. We can also insert the expressions obtained for the image charges q prime and q double prime into the second and third terms of the electric potential phi. The result shows that the potentials of the grounded sphere and the charged one only differ in the third term, representing the contribution of the second image charge. This can be seen in the case of the electric field strength E at the point P as well. The components of the electric field in the spherical coordinate system adapted to the x-axis are the same as those of the field derived in the example with the grounded sphere. The only difference is the contribution of the Coulomb force produced by the image charge q double prime in the radial component of the field. This force term is proportional to the image charge q double prime over the cube of the distance r between the image charge and the point P. As the vanishing azimuthal component indicates, the electric field is still axially symmetric about the x-axis since all the three charges q prime and q double prime are on this axis. The principle of superposition can also be applied to determine the electrostatic force exerted on the charged sphere by the point charge q, where we calculate the force F exerted on the sphere by the point charge as the superposition of the Coulomb forces acting between the charge q and the two image charges q prime and q double prime. The first term describes the force acting between the point charges q and q prime at the distance of x sub plus minus x sub minus given by 1 over 4 pi times epsilon naught times q time q prime over the square of distance of x sub plus minus x sub minus. The second term represents the Coulomb force between the point charges q and q double prime at the distance x sub plus, which is equal to 1 over 4 pi times epsilon naught times q double prime over the square of distance x sub plus. We already expressed the first term in the terms of the charge q, the distance x sub plus and the radius capital R in the example with the grounded sphere, and we obtained minus 1 over 4 pi times epsilon naught times x sub plus times capital R times q squared over the square of the difference between x sub plus squared and capital R squared. We can also substitute the expression obtained for q double prime into the fraction in the second term, and write it as 1 over 4 pi times epsilon naught q times the sum of q naught and capital R times q divided by x sub plus over x sub plus squared. The opposite signs in the front of the two terms show that the force attracting the charged sphere is reduced by the electric field due to the constant charge q naught over the sphere. Now we discuss the example of a point charge near a conducting sphere with constant voltage. We consider the case of the sphere of constant voltage phi naught, where the point charge q in the volume V is outside the sphere of radius capital R at the distance x sub plus from the center of the sphere. The method of images is applied again by placing an image charge q prime inside the conducting sphere with the volume V prime at the distance x sub minus from the center on the x-axis connecting the point charge q with the center. The distance x sub minus is still equal to the square of the radius capital R over the distance x sub plus, and the image charge q prime is given by minus the ratio of capital R to x sub plus, times q. Since the potential on the sphere is equal to the constant phi naught, we need to introduce another image charge to produce an electric field over the union of the volumes V and V prime such that the conducting sphere is still an equipotential surface of potential phi naught. If we place a new image charge q double prime in the center of the sphere, we can apply Coulomb's law to determine the amount of the second image charge, which tells us that the potential phi naught is equal to 1 over 4 pi times the vacuum permittivity epsilon naught, times q double prime over capital R. Then the image charge q double prime can be written as 4 pi times epsilon naught times the radius capital R times the potential phi naught. The electric potential due to the 3-point charges is given by the superposition of the Coulomb potentials of the individual charges. As in the previous case, the potential phi at the point P at the distances R sub plus, R sub minus and R from the inducing charge q, the image charge q prime and the image charge q double prime can be written as 1 over 4 pi times epsilon naught, times q over R sub plus 1 over 4 pi times epsilon naught, times q prime over R sub minus, plus 1 over 4 pi times epsilon naught, times q double prime over R. The square of the distance R sub plus or minus is equal to the square of the distance R, plus x sub plus or minus squared, minus 2 times R times x sub plus or minus times cosine theta. Since the first two terms of the potential vanish over the sphere for the expressions for x sub minus and q prime shown here, the potential over the sphere is equal to phi naught, as expected. We can also insert the expressions obtained for the image charges q prime and q double prime into the second and third terms of the electric potential phi. Again, the result shows that the potentials of the grounded sphere and this sphere only differ in the last term, here capital R over R times phi naught representing the contribution of the second image charge. The components of the electric field E in the spherical coordinate system adapted to the x-axis are also the same as those of the field derived in the example with the grounded sphere. The only difference is the contribution of the Coulomb force produced by the image charge q double prime in the radial component of the field. This force term is proportional to the image charge q double prime over the cube of the distance or between the image charge and the point P. The electric field is still axially symmetric about the x-axis because all the three charges q prime and q double prime are on this axis. The principle of superposition can also be applied to determine the electrostatic force exerted on the conducting sphere of voltage phi naught by the point charge q, where we calculate the force F exerted on the sphere by the point charge as the superposition of the Coulomb forces acting between the charge q and the two image charges q prime and q double prime. As in the previous example, the first term describes the force acting between the point charges q and q prime at the distance of x sub plus minus x sub minus given by 1 over 4 pi times epsilon naught, times q time q prime over the square of the distance of x sub plus minus x sub minus. The second term represents the Coulomb force between the point charges q and q double prime at the distance x sub plus, which is equal to 1 over 4 pi times epsilon naught, times q double prime over the square of the distance x sub plus. The first term is given by minus 1 over 4 pi times epsilon naught, times x sub plus times capital R times q squared over the square of the difference between x sub plus squared and capital R squared. By substituting the expression obtained for q double prime into the second term, we obtain capital R over x sub plus squared, times q times phi naught. As in the case of the sphere with constant potential, the force attracting the charged sphere is reduced by the electric field due to the constant non-zero potential phi naught over the sphere.